everyone. So our next video or next slides start to move into equilibrium constants, and this becomes a way that chemists can kind of numerically measure which side is going to be favored, and allows them to also kind of figure out some key points or key parts within different equilibrium reactions. And so we'll take a look at a couple different examples. So chemists can express the position of equilibrium in terms of numerical values, and these values relate the amounts of reactants to products at equilibrium. In general, at equilibrium, we kind of have this set equation. Now, keep in mind that there may be more or less with each one, but basically the larger letters, the capital letters, they represent elements or compounds that are present. The lowercase letters, like A, B, C, and D, they represent the coefficients, or they represent the number of moles that are present. So most equations kind of follow this template. And so at equilibrium, we kind of have this idea for a reaction. The equilibrium constant, KEQ, is the ratio of product concentrations to reactant concentrations at equilibrium. So capital K and then lower subscript EQ. So the expression to solve for the equilibrium constant looks a little bit like this. Okay, so KEQ is equal to the products on the top and the reactants on the bottom. Now notice that the coefficients in the balanced equation, they become powers of. So they're not multiplied by, they become squareds or cubes or to the power 4 or so on. A and B and C and D, the capital letters that are there, they represent the concentration of the substance in moles per liter. Now, you may also see somewhere along the line that moles per liter also has its own general term, and that's called the molarity. So moles per liter represents molarity. Its value is just a capital M. So these are interchangeable units that we can use as well when we deal in concentration values, because it's always how many moles are there per 1 liter of that substance. So if the temperature of the reaction changes, then KEQ also changes. And that's really important because for the most part we consider temperature for these reactions to be at like 25 degrees Celsius. But if you remember going through Le Chatelier's principles, it says that the stress of temperature can cause an equilibrium shift to the left or to the right based on if temperature is added or if things are cooled down. And so when we measure KEQ, it actually, the same reaction can have different equilibrium values based on the temperature that it's at currently. So most of the time for common reactions, we keep things at room temperature so we can get reliable comparisons. So if KEQ is greater than 1, then that kind of indicates that the products are favored at equilibrium. And similarly, if it's less than 1, then the reactants are favorable at equilibrium. So as an example problem, the colorless gas dinitrogen tetroxide, which is N2O4, and the dark brown gas nitrogen dioxide exist in equilibrium with each other. So we have N2O4 and 2NO2. And then it says a liter of gas mixture at equilibrium contains, at 10 degrees Celsius, contains 0.0045 moles of N2O4 and 0.30 moles of NO2. And then it wants us to write the expressions for the equilibrium constant and calculate the equilibrium constant KEQ for that reaction. So I'd like for you to pause the video and take a look at the equation, see if you can set it up and how far you can get. And then if you can get it, great, come back and we'll go through. And if you get stuck, come on back and we'll see if we can't figure out where you might have got stuck and try to get you going a little bit forward. So pause the video, give it a try, come back when you're ready. All right, so for our first one, remember that we have our reactants and our products. And so products go on the top, reactants go on the bottom. And in this case, we're really referencing right here. So really, we only have one term in the reactant side compared to one term in the product side, right? There'd be like no B, for instance, or no D from our equation from before because we only have one thing. So let's take a look and see what this is going to be. So we can say KEQ is equal to NO2, and that's going to be squared because it had a value of 2 in front of it for its moles, so its coefficient was 2, and that's over N2O4. So KEQ is equal to, and then I have 0.030, now moles per liter, right? Which we also said earlier was molarity as well, and then I need to remember that that has to be squared. That's going to be all over 0.0045 moles per liter, and that one just had a value of 1 in front of it, so in this case I don't have anything else. Now I take 0.03 and square it, and divide it by 0.0045, and I get a KEQ value that's 0.2, but then I have to look at significant digits. There's 2 here, there's 2 here, so there's 2 in my answer. Moles per liter. Now in this case, what we're seeing here is that KEQ is less than 1, so that's kind of indicating here that the reactants are favored. Alright, so example 2. In this case, similar kind of setup again. 1 mole of a colorless hydrogen gas and 1 mole of violet iodine vapor are sealed in a 1 liter flask and allowed to react at 450 degrees Celsius. At equilibrium, I notice that we have 1.56 moles of colorless hydrogen iodine being present, together with some of the reactant gases. And it's this part right here that kind of tells us we have an equilibrium reaction. Right, so we still have some of these gases left over, but they were able to make 1.56 moles of colorless gas with them. And it wants us to calculate the KEQ for it. So I'll get you to pause the video, see if you can set up the equation, read it through, see if you can get it to work out for you to come up with an answer. And like before, if you get stuck, come back, we'll go through, and if you get it, come back and we'll check to see if you're on the right track. Alright, so this one has a little bit of a kind of thinking problem through it, and you probably got stuck trying to figure out the moles of hydrogen and iodine for their gases. So notice that when they start, it says 1 mole of colorless hydrogen gas and 1 mole of violet iodine vapor are sealed. And so I've got 1 mole that I'm starting for each one of these. Right? And then we don't have any of this yet. And then after the reaction happens, okay, they're allowed to react at 450 degrees Celsius, so like at a really hot temperature. After the reaction, what we notice is that this thing then has 1.56 moles of the hydrogen iodide. So that means that there must be 0.44 moles left over that are still present with some of the reactant gases. Now, each of these are in equal concentration, 1 mole and 1 mole. So if I have 0.44 moles left, then they would each equally be split because they're in equal proportion to each other. So that 0.44 moles really breaks down to 0.22 moles of each one of them. And then once we have that, we should be able to run through our equilibrium calculations. So it's just kind of that understanding how to determine the number of moles that would be present given this equilibrium reaction. So we'd start off and we'd have our KEQ equation. So KEQ is equal to, and then I've got my hydrogen iodide. Remember, there's 2 moles of it, so it's going to be squared. And that's over top of H2. There's no power for that one. And that's multiplied by I2 in my reactant spot. And then I plug in my values, so KEQ, I know I have 1.56 moles per liter, and it's going to get squared. That's all over top of H2, which we know is 0.22 moles per liter, and I2, which is also 0.22 moles per liter. And so KEQ in this case, once I square it and divide it by 0.22 and times 0.22, that gives me a value of 50. And so significant digit wise, I'd say that 0 would count. So really, I could also write this out like 5.0 times 10 to the 1 in terms of its KEQ value. And this says that KEQ in this case is greater than 1. So, and we could kind of see that anyway from the molarity values that we have. But in this case, the products are more favored than the reactants are. So let's run through one more example here. So we have bromine chloride, which decomposes to form bromine and chlorine. And here we can see our equation for 2BrCl gives Br2 and Cl2. At certain temperatures, the KEQ for this reaction is 11.1. So pure BrCl is placed in a 1 liter container, so there's our 1 liter mark again. And it shows that the reaction mixture contains 4 moles of Cl2. So how many moles of Br2 and BrCl are also present in the equilibrium mixture? So similar to the last one, pause the video, see if you can set up the equation to start with, and see how much of it you can kind of fill in. And if you get stuck, come on and we'll go through. And if you can solve it, then come on back and we'll check it and see how you did. All right, so with this one, we have this container that's 4 moles of Cl2. And so we know that we have 4 moles here. And then from the last question, hopefully maybe you're able to kind of infer or realize that we have a KEQ value. Okay, so we have a final value of 11.1. And I don't know what this is, and I don't know what this is. But because each Br2 and Cl2 have 1 mole in them, then their proportions are going to be the same in terms of the concentration that they have in this reaction. So if Br2 has 1 mole and Cl2 has 1 mole, then it's fair to assume that this is going to have 4 moles as well. And then once I see that this has 4 moles in it, and I have all the other information other than BrCl, that means that I can solve for that value. So I'm going to set up our KEQ equation. So KEQ equals, and I have my bromine gas and my chlorine gas, and that's all going to be over that BrCl, and it was squared. Now, a formula rearrangement here would just mean that I'd have to rearrange for BrCl2, or BrCl squared. And so I would actually have to multiply by that part on the top on both sides and then divide by the KEQ. When I do that, I get BrCl squared is equal to Br2, Cl2, all over my KEQ value. And then I just plug in the information that I have. So BrCl, I have 4 moles of each one of them, so 4.00 moles per liter, and 4.00 moles per liter, all divided by 11.1. So that means that 4 times 4 is 16, 16 divided by 11.1 gives me 1.44 moles per liter. And then that means that this is still squared. I need to take the square root of both, so I can cancel out that squared term, which means the concentration, or the molar concentration of BrCl is going to equal 1.20 moles per liter. So that gives you a couple of different examples in setting up a few different things, from reversible reactions to Le Chatelier's principle to calculating KEQ variables. So there's a couple of questions for you to try out that are in the book, and let me know if you have any questions.